Okay, you should be on page 14 of your lecture notes. And now we are going to derive an equation to relate the macroscopic quantities of the gas with the microscopic quantities of the gas. And this is PV equals to 1/3 nmc square. This will be the final equation that you will need to derive to, where P is the pressure of the gas, V is the volume of the gas. These two are the macroscopic quantities, and N is the number of gas molecules, M is the mass of each gas molecule, and this C square is the mean square speed of the gas molecule. And we are going to introduce this term, mean square speed of the gas molecule, at the later part. Right, so remember that this is the final form and we need to derive this equation. Okay, before we start deriving, there are some assumptions of the kinetic theory of gases that you need to know, right? You will be asked to state some of them in paper 2 or paper 3. So you need to memorize them. Um, Number one, the first assumption is that a gas consists of a very large number of gas molecules. Of course, this picture doesn't show that large number. This is just a representation, right? So the gas must consist of a large number of molecules. Two, the gas molecules are in constant random motion. Now, if you look at this, well, you can see that the molecules are moving in random directions. And throughout the whole motion, it obeys the Newton's law of motion, right? Number three, the collisions between gas molecules are elastic. So I hope you remember in topic 3, what's the difference between elastic and inelastic collision. Elastic collision means that the kinetic energy is conserved, right? And the collisions between gas molecules and the walls of the container are elastic, right? So for example, if this molecule were to hit against this wall, right, with a speed of 5 meter per second before the collision with the wall. So after collision, right, what is the speed of the molecule? It should also be 5 meter per second, so that the kinetic energy of the system remains the same. Okay, that's what it means, and this is an important assumption in the derivation of the equation. Okay, for the fifth assumption, um, intermolecular forces act only during collisions, and the duration of a collision is negligible compared with the time interval between collisions. So what does this mean? So if let's say the molecules do not collide, if let's say they can just move freely without any collision, there will not be any intermolecular forces acting on them, and the duration of the collision is negligible. So if I look at here, it means that the molecule is only in contact with the wall for a very, 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 very short period of time, and so we say that it's negligible as compared to the time between collision. So let's say, just hypothetical, it takes 10 seconds to reach to this wall before it collide again, right? So that is the time between collision, um, and it's only in contact with the wall. That means the wall exert a force on the molecule only for say 0.000001 second. So as you can see, the duration of the collision, which is in contact with the wall, is negligible compared to the time interval between collisions. Okay, this is also another important assumption that we have to make in order for us to get the average force. Okay, so for assumption 6, the volume of the gas molecules themselves is negligible compared with the volume occupied by the gas. What does this mean? This means that if let's say all the molecules, if you put all the molecules together to form a ball like this one, form a ball, you will find that the space that it occupy, the space that all the molecules combined, the volume that it occupy is negligible compared to the entire volume of the gas, which is the volume of the container. So what can you say about the gas? You can say that almost all the gas is empty space, right? It's made out of empty space. Okay. And for assumption 7, between collisions, a molecule moves with uniform velocity, which is aligned to assumption 5, because we say that there's no intermolecular forces acting on them when there's no collision. So they should move with a constant speed and direction, which is also aligned to obeying the Newton's law of motion, Newton's first law. Okay, so with these 7 assumptions, we can now proceed to derive the equation PV equals to 1/3 nmc squared. Okay, so now we are ready to derive the equation PV equals to 1/3 nmc squared. In this equation, you can see that there's pressure and there is speed of the molecule. So we have to think of a way to relate the pressure with the speed of the molecule. And so the thinking process will be pressure is related to force, right? The pressure of the gas is related to the force that it exerts on the wall. And the force can be determined by looking at the change in momentum of the molecule. Now this change in momentum is where the speed comes in, right? Because momentum is mass times velocity. So it will have the speed term inside this change in momentum of the molecule upon collision with the wall. So how what we are going to do is that a molecule moves and hits the wall, and there's a change in momentum experienced by the molecule, and then we can determine the force experienced by the molecule, and by Newton's third law, I will know what is the force experienced by the wall, and that's pressure, right? We divide by the unit area, we will get the pressure of the gas, right? And that's step 1. And step 2, you will see that in the analysis in step 1, we only consider one direction to make it easier, simpler, right? So we will consider only one direction. Then in step 2, we will further analyze it in a 3-dimensional way, so that we get this final equation, right? So how can we analyze it in a 3-dimensional way? We have to make use of the assumption that the motion is random. So the gas can move in random direction, and there is a large number of molecules. Then we can use Pythagoras theorem, which later we are going to introduce it, right? And make further modifications to the equation to represent the total pressure exerted on the wall, and it will be in this final form. Okay, so remember the big picture. We have the step 1 trying to have the equation with pressure and the speed of the molecule, and then we further analyze it in a 3-dimensional way to have to come to this final equation. All right. Okay, so we consider a cube of side L. So this is a cube of side L, and it contains n number of molecules. So there are n number of molecules, a lot of them, of an ideal gas, each of mass m. Okay, and there are a lot of molecules. They are all in random motion, moving in different direction with different speed. Okay, and we just pick one of them, this molecule, right? It has a velocity in this direction, and the magnitude of the velocity is v, right? The speed is v. Now this velocity can be resolved into uh, 3 components. Now usually we only talk about x and y component, right? But now we are considering 3D, so there's also a z component, right? Now if we were to analyze it like this, it's going to be very difficult. So what we are going to do is we are just going to focus on one component, right? Vx. Now In this derivation, we are going to change the symbol V to C, right? Not much of a difference, right? Just that now the velocity is represented by the symbol C, okay? Right, so remember to simplify the derivation in step 1, we will just consider a molecule moving just one dimensional. So imagine we have one particle and it's moving towards the darkened wall with a speed cx, right? So it's going to move and hit the wall, and after collision, what is going to happen? It's going to move with a speed cx and it's moving in the opposite direction. So the velocity will be equal in magnitude but opposite in direction compared to the initial velocity. Why? Remember assumption 4, we were saying that the collision is elastic, therefore the speed remains the same, right? So that the kinetic energy remains the same. So now we need to look at the change in momentum. Yeah. So if I were to take rightward as positive, this was the initial velocity and this is the final velocity. The speed remains the same, and therefore the change in momentum is momentum final minus momentum initial, and that will be minus or negative 2 mcx, right? Remember there is a vector quantity, momentum is a vector quantity, therefore this negative sign is important. Okay, now we have come to the conclusion that the change in momentum is negative 2 mcx. In order to determine the force on the wall, we will first determine the force on the molecule because the magnitude will be the same by Newton's third law, right? So to determine the average force on the molecule, we will use Newton's second law. And what's Newton's second law? It looks like that. Change in momentum over the time taken, right? Change in momentum we have found that is negative 2 mcx. Now what is the time taken, right? Uh, in this case, what we are going to do, the time, we would make use of the time between collisions, right? And so we need to determine the time between collisions. So remember that we have this cube and the length is L. This molecule moves from one end of the cube to the darkened wall and rebounds. We want to know the total time taken, right? So the entire time duration from the left wall to the right wall and then back, that is the time between collision, right? That is the time between the collision, and we make use of the equation speed equals to distance over time, and the time will be distance over speed. This is with the assumption 7 is moving with constant speed between collisions, right? So the distance covered is 2L, therefore the time taken between collision is 2L over Cx. Okay, this is the time taken. And so uh, previously we were saying that the change in momentum is this, and now we can substitute the change in time to be 2L over Cx. Okay, and so with that, the force on the molecule is the rate of change of momentum. We will be able to derive to this equation, right? Force on the molecule is negative m cx squared over L, and by Newton's third law, the force on the wall, which is what we are interested in, that is the pressure of the gas, is mcx squared over L. Now, so far what we have derived is the force by one molecule, right? But there are n number of molecules, right? So if we were to consider n number of molecules, the total force acting on the wall due to this n number of molecules will be now we may be thinking that the total force experienced exerted by n number of molecules will be just n times the force by one molecule, right? Just times n in here. But that is not correct. Why is that so? If we look at this graph, let me orientate you to this graph. The vertical axis is the number of molecules, and the horizontal axis is the speed, right? So as you can see, at different temperatures, at let's say 0 degrees Celsius, there is a spread of the speed, right? There's a spread of the speed. That means there will be molecules with this speed, there will be molecules with this speed, with this speed, with different speed. Just that the average speed, somewhat the average speed is lower than the average speed at 1000 degrees Celsius, and at 2000 degrees Celsius the average speed is larger. Okay, so from here we can see that there's a spread of the speed, right? Therefore we cannot just have n times the force by one molecule, because with different speed the force exerted by different molecules will be different. Hence we need to make use of the average speed, so called, right? So if we look at this equation, right, what it tells us, the force exerted by n molecules is, this is the force exerted by the first molecule with speed of the first molecule, plus the force exerted by the second molecule with the speed cx2, which is different from cx1, plus other molecules, n molecules, right? And if I were to factorize it, take the m over l out, I will see that there is this, basically I will need to sum up the square of the speed of all the molecules, right? The square of the speed of all the molecules, n molecules, okay? Now, I have mentioned we want to find the average speed, right? But it's not so simple. So we are going to introduce a term called the mean square speed. Now this mean square speed, from the term, it means the mean or the average of all the square speed. Okay, so this is how it can be written in mathematical form. Let's try and understand this. This is the symbol for mean square speed, right? This bracket means is mean or average. Okay, so it's the mean of whatever that is inside, which is the square speed. So it's the mean square speed is equals to the square speed of the first molecule plus the square speed of the second molecule plus the square speed of the n molecule, yeah, dot, 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 divided by all the molecules, n number of molecules. That will be the mean square speed. Now we are going to introduce, we have to make use of this term, right? And if I were to bring the n over to the left hand side, this is what we have, okay? And if you look closely over here, this is what we had previously, okay? This is what we had previously. And so now, after introducing this mean square speed, I can make use of this term to replace this. And that means that the total force acting on the wall due to the n number of molecules will be reduced to this, right? N m over L, the mean square speed, okay? Now, once we have gotten the force, to get the pressure is simple, right? The pressure exerted by n molecules on the darkened phase is then given by pressure equals to force over area. The force we have found earlier on divided by the area L square. And if we combine this L square with this L, what we get is volume, right? So as you can see, there's a P and there's a V, right? And we are getting closer to the final equation that we should have, right? Okay, so remember, there's a second step of the derivation. So far, we have covered the first step in getting the pressure of just the molecule moving in one dimension. So now we have to consider three dimension. Three dimension, um, back to this diagram, right? The molecule actually have a velocity in this direction, but it can be resolved into Cx, Cy, and Cz components, right? Okay, so now we can apply Pythagoras theorem to the 3D velocity vector for any molecule, and that will lead to this equation: c square equals to cx square plus cy square plus cz square. Now I think you are familiar with the Pythagoras theorem, a square equals to b square plus c square for the triangle, right? Now that is Pythagoras theorem applied to a 2D vector, two-dimensional vector. But when it's applied to three-dimensional vector, it's just additional of one more direction, okay? So I hope you can find the similarity between what you know and what you are learning now, or what you are seeing now, okay? Now the next step, uh, we can also say that the mean square speed of the velocity vector, overall velocity vector, is equals to the mean square speed of the x component and the mean square speed of the y component and the mean square speed plus the mean square speed of the z component. Now from this first step to the second step, right, you do not need to know how it's being derived, right? It is not required for the physics syllabus, but if you are interested, you can read up on it on Pythagoras theorem as to why from the first equation you can reach the second equation, right? So for physics, for the derivation, you just need to know this. And when n is large, right, and the molecules are all moving randomly with no preference in any direction, we can see that the x component of the velocity, the mean square speed, is equals to the y component, mean square speed, is approximately equals to the z component, the mean square speed of the z component. And with this and this, these two equations, you can see that 3 times of Cz is equals to C square, right? Because this is approximately equals to this, equals to approximately equals to this. So 3 times of this is equals to this, okay? And therefore, you can write this form, which is the mean square speed of the x component is approximately equals to 1/3 the mean square speed of the velocity vector. Okay, so this is from part 1. We obtain the equation that relates the pressure with the velocity in the x component. And then in part 2, we derive this equation where the mean square speed of the x component velocity is approximately or equals to 1/3 the mean square speed of the velocity vector. With these two, when I combine it, this is the ultimate equation that you need to derive. PV equals to 1/3 nm c square. And of course, this is a new term that you must be familiar with. Is the mean square speed, mean of all the square speed of the molecules. And if we define another new term, which is the root mean square speed, what's the difference? Basically, there's a root in front of the mean square speed, so I will square root the mean square speed. So this is the mean square speed, and I will just square root it. And this is the symbol for root mean square speed. Okay, so how do I read this? The root mean square speed of the molecule is equals to square root of the mean square speed. Okay, so if I introduce this root mean square speed, uh, this is what I will have, right? 1/3 nm root mean square speed square. Because if I square the root mean square, I will get the mean square speed. Okay, so with that, these are the two equations that you must be familiar with. And for this equation, it's not just the derivation. You also need to know how to apply it in subsequent examples and the tutorial. So the summary of the derivation, I know is a lot of steps involved, right? So I hope this summary helps. What is the thinking process and what leads to another, from one step to another, right? So first we consider only the component of the velocity in the x direction to make it simple. Okay, just one molecule in the x direction. Then I need to have the pressure and the speed in the equation. So I will use Newton's second law, right? And then I will determine the change in the momentum of the molecule when it hits the wall. I need to know the time taken. Why is that so? Because ultimately, the change in momentum over the time taken between collision will give us the force, the average force. And I will use Newton's third law to obtain the force on the wall. And this is the intermediate step, right? You should derive this intermediate step. Then you consider n number of molecules, and that is where we start to introduce the mean square speed, right? Because not all molecules have the same speed, right? So we need to introduce the term mean square speed. And then we make use of the pressure equals to force over area to get this. Up to here is part 1 of the derivation, right? Where we only consider the x direction. Okay? Then we consider all components of the velocity, right? 3-dimensional, and use Pythagoras theorem. We get this final equation where we don't only consider the x direction, but we consider the entire velocity vector. Okay?